The goal for any course on group theory is to get to know the structure of groups. What can we say about the properties that make two groups different from one another, for example? And one of the most intimate properties that we can learn about a group is what kinds of subgroups does that group have? What are the smaller building blocks that make up my parent group? If we can answer that question, we learn a lot. Now, for cyclic groups, we have these two models for what cyclic groups look like. Infinite cyclic groups look like a number line. They look like the additive group of integers. Finite cyclic groups look like a clock. They look like the additive group of integers mod n, where n is the finite order of that group. And so, because those two models seem very concrete, they seem like things we can get our hands around because we understand integers and we understand addition of integers mod n very well, that means that we should be able to come to a very quick understanding of the properties that cyclic groups enjoy because they fall into one of those two models. So step one is going to be to discover a relationship between the order of a cyclic group, how many elements it has, and the order of the elements inside that group. How many powers of them does it take to make the identity? So that's the first step in this video. So just to get our feet back on the ground, remember that to say that a group is cyclic means that there exists an element in that group. We're going to call it A through this series of videos. We call that element a generator for the group. And it has the property that every element of the group is a power, is some power, is the iterative application of the group operation to that same element repeatedly. Right, so A to the power n is equal to g. Right? Every g, every little g, which is an element of this group, is some power of the generator A. And we've seen some examples of cyclic groups. In the introduction, we mentioned that addition modulo n is a perfect model for a cyclic group. So, for example, addition modulo 6 of residue classes of integers mod 6 is a good example of a cyclic group. And an example of a generator for this group would be the element 1, or the equivalence class of 1 mod 6. And it's a generator because if I look at its powers, the first power of it, the second power of it, the third power of it, keep in mind here that I'm using the word power to mean the iterative application of the group operation, which is why to the second power means 1 plus 1 mod 6. But if I look at all the set of powers of that single element, they are going to account for all the elements in my group. As soon as I get to the sixth power, 1 added to itself 6 times, I am back at the residue class of 0, which is the identity element in my group. And so I can account for all the elements of this group by taking powers of the element 1. And so what you notice is that the order of this element is 6, because the first power is not the identity, the second power is not the identity, neither is the third, the fourth, or the fifth power, but the sixth power is. But it's not the only generator that we could come up with for this cyclic group. What about 5? If I look at the iterated powers of 5, 5 to the first power, 5 to the second power, third power, fourth power, and so on, what elements would that account for? Well, the first power is going to be 5, but the second power, 5 plus 5, mod 6, it's 10 mod 6, that's 4. 5 added to itself 3 times, 15 mod 6, that's 3. 20 mod 6 is 2. 25 mod 6 is 1. And then 30 mod 6, we're back to 0. So the powers of 5 in this group have accounted once again for all of the elements in my group. They've just done it in kind of a different order than 1 did, but that's okay. So 5 also is a generator for the additive group of integers modulo 6. And its order is also 6, because the first power, second, third, fourth, and fifth power of 5 are all not the identity element, but the sixth power is. And so you might say, well, this is great. Now we have 2 possible choices for generator inside of this cyclic group. Are there others? And it turns out that for this group, the answer is no. To see why, let's suppose I pick another element like 4. What are the powers of 4? What elements do those account for? Well, 4 to the first power is going to be 4. 4 to the second power, that's 8 mod 6 is 2. 4 to the third power, 12 mod 6 is 0. And then when I come back to 4 to the fourth power, I get the equivalence class of 4 again, 2 again, 0 again. And so the powers of the element 4 account for 3 out of the 6 elements only. The 0 element, the 2 element, and the 4 element. But the 1, 3, and 5 are never accounted for in these powers. If you're thinking about number theory, you might see that the reason why is that any iterative power of 4 is going to be an even integer, and an even integer mod 6 is always going to be an even numbered equivalence class, 0, 2, or 4. So there's no way for us to get one of the odd equivalence classes, 1, 3, or 5. And so the element 4 is not, in fact, a generator. for Z mod 6, because it only gives us 3. Its powers only give us 3 out of the 6 elements in this group. As we said in our introductory video, the integers, in general, additive group of integers without a modulus, just the integers that we learn how to add in 2nd grade, that group is also a cyclic group, because there exists an element, all of whose powers will generate the integers. That element is the element we call the number 1. And so, if I take 1 and I add it to itself, I get 2. If I do it again, I get 3. If I do it again, I get 4, and so forth, and so forth, and so forth. That is going to account for all of the positive integers. But then also, we can account for the negative integers just by taking negative powers. And we can account for 0 by taking the 0th power. Again, remember, these powers are applications of the addition operation. So, to say 1 to the power negative 1 really is just to say the inverse. And in my group here, the inverse is the inverse under addition. So it's the additive inverse of 1. Additive inverse of 1 is negative 1. So don't, again, get turned around by the notation that we're using. It looks like exponentiation, but it really just means apply the operation of the group repeatedly. And so what we see is that the negative powers of 1, which are exactly the multiples of its additive inverse, negative 1, will account for all the negative integers as well. And so the number 1 is a generator for the cyclic group of all integers. This is an infinite cyclic group. And so, again, mental model, it looks like a number line. Of course, 1 is not the only generator for the group of integers. We could also just as well have chosen negative 1 as a generator, because its powers will account for all the negative integers. Its inverse powers will account for all the positive integers, and the 0th power will account for the identity element. All right, here's another example that's a little bit less straightforward. How about the multiplicative group of units mod 10? So these are the equivalence classes mod 10 that have multiplicative inverses. And it turns out that this consists of just the equivalence classes of 1, 3, 7, and 9 mod 10. If we write out the Cayley table for this, then we can see why this turns out to be a cyclic group. For example, 3 happens to be a generator. The first power of 3 using my Cayley table is 3. The second power of 3, 3 times 3, gives me 9. The third power, 9 times 3, is going to give me 7. And then the fourth power, 7 times 3 again, is going to give me 1, which is the identity element in my group. And so 3 has generated all the elements in this group, and therefore is a generator for this group. Its order is 4. In the same way, 7 is also a generator. Alright, but this video wouldn't be complete without an example of a group that's not cyclic. So how about the multiplicative group of integers modulo 12 instead of modulo 10? If we write down a Cayley table for that group, having the equivalence classes of 1, 5, 7, and 11 as its elements, let's go through the process and figure out what elements each of these generate when we look at its set of powers, the iterative applications of the group operation. Which in this case, since our group operation is a familiar multiplication of integers, then the exponents that we're using to denote these powers also do mean powers in the traditional sense of exponents on the integers. So what does 1 generate? 1 to the first power gives me 1. To the second power is 1. To the third power is 1. To the fourth power is 1. To the fifth power is 1. So the set of powers of that is just 1. So the order of that element is 1. This is true for the identity element of any group. By definition, its order is equal to 1. Well, what about the element 5? 5 to the first power is 5. 5 to the second power is 1. And then 5 to the third power will be 5 again. 5 to the fourth power will be 1. And so on and so on. So we can only generate 1 and 5. It turns out the same is true for 7. 7 to the first power is 7. To the second power is 1. To the third power is 7. And to the fourth power is 1 again. And so on. Same is true for 11. So it turns out that in this group, we have elements of order 1, and we have elements of order 2. But that's it. None of my elements in this group are capable of generating all 4 elements of U12. And therefore, we've, by explicit brute force, ruled out the possibility that U12 is a cyclic group. So this is our set of basic ideas and facts about cyclic groups. What I want to do now that we've sort of gotten back into the headspace with these specific examples is see some more general properties that every cyclic group will enjoy, talk a little bit through why they're true, and at least in one case, sketch out a proof.